So now that we've carried out a chi-squared test for a monohybrid cross, now we need to step it up and do it as a dihybrid cross, which is a skill you're expected to attain. So here's an example. It's a dihybrid cross, therefore it has more than two categories or traits. So we have a purebred white chicken with a single comb versus a dark chicken with what's known as a P-comb. So a note here for you is that white in terms of the feather colour is dominant to dark, and the P-comb, the shape on top, is dominant to a single comb. So when you cross these two, all of the offspring you will find are white with a P-comb, heterozygous for both traits. You can actually carry this out yourself on paper if you'd like to practice your dihybrid cross. I would encourage it. Now if we look at the next generation, we're going to take the offspring, which are the white with the P-combs, heterozygous for both. Now we want to use this to carry out an unlinked genetic cross with these two chickens, heterozygous for both traits, and determine the expected phenotype ratio of the offspring. This is excellent practice for you to practice a dihybrid cross. So pause the video at this point and carry out a dihybrid cross. So here you can check your answers for the expected phenotype ratio for a dihybrid cross. It's also excellent review. So we have our two chickens here, heterozygous for both traits. We have a reminder that white is dominant to dark. In this case, I've used F to represent that gene. And a P-comb is dominant to single comb. I've used a B to represent that gene. So we can see that the genotypes of both of them are capital F, lowercase f, capital B, lowercase b. And because these traits we're proposing are unlinked, you can see that they're on separate chromosomes as illustrated here. So if we take it from there, we can see the gametes represented below. However, independent assortment is possible. Therefore, you could also have the following gametes. And if we put all of those into a Punnett square, then we actually have a 4x4 Punnett square. So there's quite a lot of offspring to analyze here. Let's take a look. Now, once you've checked and double-checked your answers here, you can try to analyze all of the offspring for the phenotype ratio. That's what we care about here for our chi-squared. It's also a phenotype ratio that becomes quite well known when you have two individuals that are heterozygous for both traits in a dihybrid cross. So, white with P-combs, 9 out of 16. Dark with P-combs, 3 out of 16. White with a single comb, also 3 out of 16. And dark with a single comb, 1 out of 16. Notice that the two dominant traits, the white and the P-comb, always give the 9 out of 16. The dominant with a recessive trait, either dark with P-comb or white with single comb, is always a 3 out of 16. And the two recessive traits, dark and single comb, that's always the 1 out of 16. So if we did this and we actually took a look at the offspring, then what if that's not what we got? That in fact, out of 190 offspring, this is what we got. We expected 9 to 3 to 3 to 1 of the ratio if the traits were on different chromosomes. But we actually got this data. So the observed ratio is different. So how can we determine whether there is or is not a significant difference between the observed and the expected? So is the difference that we are observing between the observed and the expected, is it not statistically significant? It's actually just due to chance, and certainly these genes are unlinked and they do assort independently? Or is it possible that this is actually a statistically significant difference? And if it is, then maybe these traits are not unlinked. They're actually linked and they don't assort independently. And this is what we're going to try and deduce the answer to. So these are the two possible hypotheses. The null is that there is no statistically significant difference. The traits are not linked, they assort independently. Versus the alternative, there is a statistically significant difference, that actually the traits are linked. They're on the same chromosome, and therefore they don't assort independently. So now how do we calculate the chi-squared value for a dihybrid cross? It is exactly the same as the monohybrid cross. So we'll follow the same steps. So reminder here of what we actually observed in that second generation F2 generation. So we draw ourselves a table exactly the same as before, but notice that the difference now is that the categories we see are now indicating two different features, the color, light or dark, and the p-comb versus the single comb. So our categories include details about both of the different traits. So here is our observed data in there, out of a total of 190 individuals, offspring from there. So if we think about our expected data is still that 9 to 3 to 3 to 1 ratio. So 9, whereby we have both dominant traits, 3 in both of the cases where we have a dominant with a recessive trait, and 1 where we have both of the recessive traits. So we're calculating this ratio, 9/16 of 190 or 3/16 of 190 in order to get our expected values. So once we have our expected values, then we can go through the steps in order to calculate chi-squared, and they're exactly as before. Notice the bottom row here. We do the observed minus the expected, we square that value, and then we divide it by expected. So we've skipped a couple of steps in the table here, but feel free to include them in your own table. And then we go about calculating chi-squared exactly as before. Notice that we sum the observed minus expected squared divided by the expected. So that last row that we just had a moment ago, we're going to add up all of the numbers on that last row, gives us 1.56. So our chi-squared value is 1.56. So does this allow us to accept or reject the null hypothesis? So let's think about our degrees of freedom. We had 4 categories in this case. So 4 minus 1, that's 3 degrees of freedom. Our probability table, 3 degrees of freedom, we use our significance of 0.05 or 95%, and therefore we have a critical value of 7.815. So in conclusion, as a result of this, our 7.815, our critical value, is compared against our calculated value, 1.56. And since 1.56 is smaller than the critical value of 7.815, we failed to reject the null hypothesis, meaning that, in fact, we have accepted the null hypothesis and there is no significant difference between the observed and the expected values. Therefore, the traits that we have observed are indeed not linked. They are on separate chromosomes and therefore they go through independent assortment. Alternately, it's worthy to consider this. If you had a situation where, in fact, you have your critical value, but your calculated value is greater than that, then we would reject the null hypothesis. So if we reject the null hypothesis, then we would be saying there is a significant difference between observed and expected values. And if there is a significant difference, then the traits that we are observing are linked as opposed to unlinked. And if they're linked, that means that they're contained on the same chromosome and so do not assort independently.